Did you know that 96% of the universe is missing? That's right, everything we see, from the stars above to the planets and galaxies stretching across the night sky, makes up just 4% of what's actually out there. The rest is hidden in the shadows, a cosmic mystery waiting to be unraveled. And that's just the beginning. The universe is full of secrets, from black holes that warp time itself to invisible forces shaping the fate of galaxies. What if I told you some of the most mind-blowing truths about space have been hiding in plain sight all along? Today, we're diving deep into the unknown to uncover 30 hidden facts about our universe that will change how you see everything. These aren't just random tidbits, they're revelations that challenge what we thought we knew about reality. Imagine standing at the edge of a black hole where gravity is so strong even light can't escape. Or picture a cosmic web, invisible threads connecting galaxies across billions of light years. The universe isn't just vast, it's alive with mysteries, each one more astonishing than the last. This isn't just a journey through space, it's a journey through the limits of human understanding. Every fact we uncover today will pull back another layer of the cosmic curtain, revealing how strange, beautiful, and utterly unpredictable the universe truly is. So buckle up, by the time we're done, you'll never look at the night sky the same way again. Ready to uncover the secrets hiding in the stars? Let's begin. Picture this, you're gazing at a star-filled sky, convinced you're seeing the universe in all its glory. But here's the unsettling truth, you're barely scratching the surface. What we perceive as the cosmos, all those glittering stars and swirling galaxies, accounts for a mere 4% of what's really out there, the rest. An invisible empire ruled by two enigmatic forces, dark matter and dark energy. Together, they make up 96% of the universe, yet they evade every tool we've built to detect them. So how do we even know they exist? Take dark matter first. Think of it as the universe's hidden scaffolding, an unseen hand shaping everything around us. Scientists stumbled upon its existence not by spotting it directly, but by noticing something bizarre: galaxies spinning faster than they should. According to the laws of physics, the outer edges of a galaxy should move slower than its center. But observations show stars at the fringes whipping around at breakneck speeds, as if gripped by an invisible force. That force, the gravitational pull of dark matter, an unseen mass weaving through space, holding galaxies together like cosmic glue. Then there's dark energy, an even stranger phenomenon. In the late 1990s, astronomers made a jaw-dropping discovery. The universe isn't just expanding, it's accelerating. Something is pushing galaxies apart faster and faster, stretching the fabric of space-time itself. That something is dark energy, a mysterious repulsive force making up nearly 70% of the universe. Unlike gravity, which pulls things together, dark energy drives them apart, and its influence grows as the cosmos expands. Here's what's truly humbling. Despite decades of research, we still don't know what dark matter and dark energy actually are. They don't emit light, absorb it, or interact with ordinary matter in any way we can measure. They're ghosts in the cosmic machine, detectable only by their gravitational fingerprints. Some theories suggest dark matter could be made of exotic particles, while others propose it's a sign our understanding of gravity is incomplete. As for dark energy, it might be a property of space itself, or evidence of entirely new physics waiting to be discovered. What's clear is this: the universe we see is just the tip of an unimaginably vast iceberg. The rest lurks in the shadows, challenging everything we think we know. And that's the beauty of it. Every unanswered question is an invitation to explore further, to peel back another layer of the cosmos's deepest mysteries. So the next time you look up at the night sky, remember, you're not just seeing stars, you're staring into the greatest unsolved puzzle of all. Imagine being near something so massive, so powerful, it literally bends time itself. That's exactly what happens near a black hole, one of the universe's most extreme and mind-bending phenomena. Thanks to Einstein's theory of general relativity, we know gravity doesn't just pull objects together, it warps the very fabric of space-time. And nowhere is this effect more dramatic than at the edge of a black hole, where gravity is so intense that time itself slows down. Think of space-time like a giant trampoline. Place a bowling ball in the center and the fabric stretches downward, creating a deep curve. Now imagine rolling marbles across that surface. They'll spiral inward toward the bowling ball, just as planets orbit a star. But what if that bowling ball were crushed into something unimaginably dense like a black hole? The curve becomes infinitely deep, a bottomless pit in space-time. Near that edge, time doesn't just flow normally, it stretches, dragging slower and slower the closer you get. This isn't just theory, it's science we've proven. Atomic clocks on GPS satellites orbiting Earth, where gravity is slightly weaker, actually tick faster than clocks on the ground. It's a tiny difference, but it adds up. Without corrections, GPS would be off by miles. Now scale that effect up to a black hole's monstrous gravity, and time doesn't just bend, it nearly stops. In the movie Interstellar, this idea was brought to life when astronauts orbiting the black hole Gargantua aged mere hours while decades passed for those far away. But here's the wild part. If you could hover near a black hole's event horizon, the point of no return, and time for you would crawl while the rest of the universe raced ahead. A minute for you might be years elsewhere. You'd watch stars flare and die in fast forward, galaxies spin like pinwheels, yet you'd feel nothing strange locally. Your watch would tick normally. Only by looking outward would you see time's staggering distortion. Why does this happen? Because gravity doesn't just pull, it changes how space-time behaves. The stronger the gravity, the more time dilates. Black holes, with their unfathomable density, take this to the extreme. They're cosmic time machines, revealing just how relative our experience of reality truly is. So next time you glance at the clock, remember time isn't as fixed as it seems. Near a black hole, it's a river flowing at different speeds, bending under the weight of the universe's darkest giants. There's a place in the universe so empty, so utterly devoid of light and matter, that it defies everything we know about how galaxies should be distributed. Stretching 330 million light-years across, the Boötes Void is a cosmic desert so vast you could fly through it for hundreds of millions of years and encounter almost nothing. To put that into perspective, our own Milky Way is just 100,000 light-years wide, a mere speck compared to this staggering emptiness. How does something like this even exist? The universe is supposed to be clumpy, with galaxies clustered together like cities connected by threads of dark matter. But the Boötes Void is the opposite, a gaping hole in the cosmic web where only a handful of galaxies drift in isolation. When astronomers first discovered it in the 1980s, they assumed their instruments were broken. Surely, they thought, nothing this big could be so empty. But repeated observations confirmed the impossible. A void so large it shouldn't exist under our current models of the universe's structure. So what could have caused it? One theory points to the early universe, a fraction of a second after the Big Bang, when space itself expanded faster than light during a period called cosmic inflation. Tiny quantum fluctuations in that primordial chaos eventually grew into the galaxies and voids we see today. If an unusually large fluctuation occurred in just the right way, it might have left behind a region like the Boötes Void, a bubble of nothingness inflating far beyond the scale of ordinary cosmic structures. But there's another, far more speculative idea. Imagine a civilization so advanced, so relentless in its need for energy, that it harvested every star and galaxy across hundreds of millions of light-years. Theoretically, a Type 3 civilization on the Kardashev scale, one capable of harnessing the power of entire galaxies, could exhaust all resources in its vicinity, leaving behind only darkness. While there's zero evidence for this, the sheer scale of the void forces us to ask, could it be artificial? Or is it simply a reminder of how little we truly understand about the universe's architecture? The unsettling truth is that the Boötes Void isn't alone. Other supervoids lurk in the cosmos, each challenging our assumptions. They're not just empty spaces, they're clues, hinting at forces or phenomena we haven't yet imagined. And that's the real mystery. In a universe teeming with galaxies, why do these enormous blanks exist at all? Every time we find one, it's like the cosmos is whispering a question we're not quite ready to answer. What if I told you the moon is slowly slipping away from us? Right now, as you read this, our closest celestial neighbor is moving farther from Earth at the rate of 3.8 centimeters every year. That's about the width of 2 pennies drifting into space. It might not sound like much, but over millions of years, those tiny increments add up to something staggering, a cosmic dance with consequences that will reshape our planet in ways most people never consider. This silent retreat happens because of tides, not just the ocean waves you see at the beach, but an invisible gravitational tug of war between Earth and the moon. As the moon's gravity pulls on our oceans, it creates bulges of water that slightly lead ahead of the moon's position due to Earth's rotation. This mismatch exerts a gravitational pull back on the moon, nudging it into a higher orbit. Think of it like a spinning ice skater extending their arms. The moon gains energy and spirals outward while Earth's rotation slows ever so slightly in response. Here's where things get eerie. As the moon inches away, Earth's days grow longer, not by much now, but over time, the effect becomes undeniable. Right now, a day on Earth lasts 24 hours, but 1 billion years ago, it was only 18. Fast forward another 1 billion years, and a single day might stretch to 28 or even 30 hours. Nights will grow longer, sunlight will linger, and life as we know it would have to adapt to an entirely new rhythm. But the most dramatic change, solar eclipses, will vanish. Today, the moon sits at the perfect distance to appear almost exactly the same size as the sun in our sky, creating breathtaking total eclipses when it passes in front. But as the moon drifts farther away, it will appear smaller and smaller until it can no longer cover the sun completely. Future civilizations might only see partial or annular eclipses, thin rings of sunlight around a dark disk, until even those fade into history. The real kicker, this isn't a one-way journey. The system is slowly losing energy through tidal friction, meaning eventually, billions of years from now, Earth and the moon will become tidally locked, facing each other like partners frozen mid-waltz. By then, the moon will hang motionless in the sky of one hemisphere while the other side of Earth never sees it at all. So the next time you gaze up at the moon, remember, you're witnessing a fleeting moment in a cosmic relationship that's been evolving for 4.5 billion years, and one that's still changing right before our eyes. The night sky isn't just a silent light show, it's a cosmic symphony. Stars don't just shine, they sing. Through a field called stellar seismology, scientists have discovered that stars vibrate like colossal tuning forks, pulsing with sound waves that ripple through their interiors. These aren't sounds you could hear with human ears. Space, after all, is a vacuum where sound can't travel. But by measuring the subtle flickers in a star's light, astronomers can translate those vibrations into audible frequencies, revealing a chorus of celestial music that's as haunting as it is beautiful. Take our own sun, for example. It hums a deep, resonant tone, its surface heaving in and out like the slow breath of a sleeping giant. These oscillations are caused by convection, the same process that makes boiling water swirl but scaled up to stellar proportions. Hot plasma rises, cools, and sinks back down, creating pressure waves that travel through the sun's interior. When scientists converted these waves into sound, they found a low, rhythmic drone like the eerie soundtrack of an underwater cavern. But the real magic happens with other stars. NASA Kepler spacecraft, designed to hunt for exoplanets, accidentally became the universe's premier music producer. By observing tiny dips in starlight caused by these vibrations, Kepler captured the songs of thousands of stars. When translated, some sound like ghostly chimes, others like a chorus of metallic sighs. One sun-like star, codenamed KC 76726449, emits a tone so clear and resonant it could almost be mistaken for a synthesizer note, except it's a nuclear furnace 100 times wider than Earth. Why do these sounds matter? Because they're more than just cosmic curiosities, they're fingerprints. Each star's vibrations reveal its inner structure, age, and even chemical composition, like a musical code astronomers can decipher. Younger stars ring with higher frequencies, their tones bright and lively, while older stars produce deeper, slower pulses. Some red giants emit waves so low they're barely audible, their dying breath stretched into infrasound. The most unsettling part, these sounds are ancient. The vibrations we detect today began their journey centuries or millennia ago, traveling through the star's dense plasma before finally reaching the surface and leaping across space as light. When we listen, we're hearing echoes from a time before telescopes, before cities, even before humans walked the Earth. It's a reminder that the universe isn't just something we see, it's something we might one day hear, a symphony written in the language of physics, performed on a stage of fire and time. Deep in the cosmic shadows, hidden behind the thick dust clouds of our own Milky Way, lurks one of the universe's greatest mysteries. A force so powerful it's dragging entire galaxies toward it at unfathomable speeds. Scientists call it the Great Attractor, and it's exactly what it sounds like, a gravitational monster we can't see, pulling everything in our galactic neighborhood toward some invisible point in space like a cosmic drain. For decades, astronomers noticed something strange. Hundreds of thousands of galaxies, including our own, are racing in the same direction at over 2 million kilometers per hour, defying the expected expansion of the universe. At first, they assumed the motion was caused by the well-known Virgo cluster, but the numbers didn't add up. The pull was far stronger than anything visible could explain. Then, in the 1980s, they discovered the truth. Something much bigger, much more massive, was lurking just out of sight, obscured by the dense plane of our galaxy. Here's what makes the Great Attractor so frustrating to study. Imagine trying to see a distant city through a thick fog. Only the fog is an impenetrable band of stars, gas, and dust stretching across our sky. Normal telescopes can't peer through it. That's where X-ray astronomy comes in. By using instruments like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton, scientists can detect the high-energy radiation emitted by superheated gas swirling around this hidden gravitational giant. What they found was astonishing. A concentration of mass so dense it rivals tens of thousands of Milky Ways packed together, warping space-time on a scale that reshapes the motion of galaxies millions of light-years away. But the plot thickens. The Great Attractor isn't acting alone. It's just one piece of an even larger puzzle. Recent studies suggest it might be the heart of the Laniakea supercluster, a mind-bending structure encompassing over 100,000 galaxies, including our own. Laniakea, which means immeasurable heaven in Hawaiian, isn't just a random cluster, it's a sprawling cosmic filament, part of the vast web that makes up the universe's large-scale structure. The Great Attractor sits at its core, acting like a gravitational anchor, drawing everything in its domain toward a shared destiny. What could possibly be massive enough to wield this kind of influence? The leading theory points to an unfathomable concentration of dark matter, the universe's invisible scaffolding, intertwined with galaxy clusters we've yet to fully map. Some speculate there might even be multiple attractors working in concert, hidden behind layers of galactic dust. Others wonder if the Great Attractor itself is being pulled toward something even larger, a structure so vast we haven't even glimpsed its edges yet. Every answer leads to more questions, but one thing's certain: this hidden force is rewriting our understanding of cosmic motion. Long after our sun burns out, long after our galaxy collides with Andromeda, the great attractor will still be there, silently shaping the fate of everything around it. A reminder that even in the vastness of space, some mysteries refuse to stay hidden forever. You'd think the vacuum of space would be odorless after all. There's no air to carry scent. But astronauts returning from spacewalks report something bizarre. Their suits smell like a sizzling grill with lingering notes of burnt steak, hot metal, and welding fumes. This isn't some cosmic prank, it's chemistry at work in the most unexpected way. When astronauts re-enter the airlock and remove their helmets, they're hit with this peculiar aroma almost immediately. Some compare it to seared beef, others to gunpowder or ozone. The source, tiny particles clinging to their suits, a byproduct of space itself. Out there, floating between the stars, are molecules called polycyclic aromatic hydrocarbons, PHs for short. These aren't just random space dust, they're the same compounds found in charred food, exhaust fumes, and even some meteorites. Here's how it happens. In the harsh environment of space, ultraviolet radiation from stars breaks down matter, leaving behind these volatile compounds. When astronauts move outside the spacecraft, their suits become a magnet for these particles. The moment they return and repressurize, those PAHs react with the oxygen inside the airlock, releasing that distinct scorched scent. It's like opening an oven door after roasting a pan. Except the oven is the cosmos and the roast is interstellar chemistry. But the weirdest part, this smell might be ancient. Some scientists believe PAHs are among the oldest organic molecules in the universe, forged in the fiery hearts of dying stars and scattered across galaxies. Every time an astronaut catches a whiff of that metallic barbecue aroma, they could be smelling the remnants of stellar explosions that happened billions of years ago. It's a reminder that space isn't just a silent void. It's a dynamic, sensory experience, even in ways we never expected. And while we can't bottle the scent of the cosmos yet, one thing's clear. If space ever opens a restaurant, it's definitely serving well-done steak. Imagine a world where the ground beneath your feet isn't rock or sand, but solid diamond trillions of carats glittering under the light of an alien sun. This isn't science fiction, it's 55 Cancri e, an exoplanet orbiting a star 40 light-years away, and it's quite possibly the most extravagant object in the cosmos. Discovered in 2004, this bizarre world is about twice the size of Earth but 8 times as dense, with a composition so rich in carbon that scientists believe a third of its mass could be crystalline diamond. To put that into perspective, if you could somehow mine it, which you can't, for reasons we'll get to, this single planet's diamond reserves would be worth more than all the money, all the economies, all the wealth ever produced in human history combined. What makes 55 Cancri e so special? It all comes down to chemistry. Most rocky planets, like Earth, form from silicon and oxygen with a sprinkle of carbon. But this planet's host star has an unusually high carbon-to-oxygen ratio, meaning the building blocks available during its formation were carbon-heavy. Under extreme pressure and heat, that carbon crystallized into diamond, creating a world that's essentially a cosmic jewel. Imagine crushing a mountain of graphite, the stuff in your pencil, until it transforms into flawless gemstone. Now scale that up to planetary dimensions and you've got 55 Cancri e. But here's the catch, this diamond isn't just lying around waiting to be collected. The surface temperature hovers around 2,700 degrees Celsius, hot enough to melt steel, vaporize rock, and turn any mining equipment into a puddle before it even touches the ground. The planet is also tidally locked, meaning one side permanently faces its star, creating a hemisphere of eternal, scorching daylight, while the other broils in endless darkness. Even if you could survive the heat, the gravity would crush you. With 8 times Earth's mass, standing on its surface would feel like carrying the weight of several elephants on your shoulders. And the absurdity doesn't stop there. Recent studies suggest 55 Cancri might have a highly unconventional atmosphere, one made not of nitrogen or oxygen but of vaporized rock. Yes, you heard that right. The searing heat could be turning the planet's surface into a bubbling ocean of molten silica, with skies filled with mineral clouds that rain liquid gemstones. Picture a thunderstorm where droplets of molten diamond streak through neon-lit haze. It's the ultimate cosmic jewelry store if you could survive the shopping trip. So why does this matter? Because 55 Cancri shatters our assumptions about what planets can be. It's a reminder that the universe doesn't play by our rules, crafting worlds so strange they defy imagination. While we'll never mine its diamonds, their very existence raises tantalizing questions. How many other diamond planets are out there? Could carbon-rich worlds harbor even wilder materials we've never seen? One thing's certain, in the cosmic casino, 55 Cancri is the jackpot no one will ever cash in. You might think the coldest place in the universe is some distant, icy planet or a frozen moon drifting in the outer solar system. But the truth is far stranger, and it's floating in the depths of space. The Boomerang Nebula, a ghostly cloud of gas 3,000 light-years from Earth, holds the record for the coldest natural temperature ever recorded, -272 degrees Celsius. That's just 1 degree above absolute zero, the theoretical limit where all molecular motion stops. To put that in perspective, it's colder than the afterglow of the Big Bang itself, colder than any laboratory freezer, colder even than the vacuum of space between galaxies. So how does something get this cold? The answer lies in the nebula's bizarre behavior. Unlike most cosmic structures which heat up as they expand, the Boomerang Nebula is doing the opposite. It's essentially the universe's largest air conditioner, chilling itself through a freakish process of hyper-expansion. At its heart lies a dying star, once similar to our Sun, but now in its final throes, shedding layers of gas at a staggering speed over 164 kilometers per second. That's fast enough to travel from Earth to the Moon in under 40 minutes. As this gas races outward, it expands so rapidly that it can't hold onto heat, cooling down to temperatures that defy logic. Hubble Space Telescope images reveal the nebula's haunting beauty, a delicate, symmetrical bow tie shape formed by the star's violent ejections. The structure isn't just cold, it's also a cosmic fridge in action. The gas is so frigid that it absorbs background radiation from the Big Bang itself, making it appear darker against the glow of the universe. Scientists call this phenomenon a natural Bose-Einstein condensate, a state of matter where atoms lose their individual identities and behave as a single quantum entity. It's the only known place in nature where this happens on a massive scale. What's truly mind-bending is that this icy relic won't last forever. As the dying star's core finally fades, the nebula will warm up, eventually blending into the interstellar medium. Right now, though, it's a fleeting glimpse of the extreme physics that govern our cosmos, proof that even in the vastness of space, nature can still surprise us with its ability to push the boundaries of cold. The universe isn't silent, it thrums with a deep, steady hum, a vibration so subtle we didn't even know it existed until recently. This isn't sound in the traditional sense. It's a symphony of gravitational waves, ripples in spacetime itself, echoing across the cosmos like the aftermath of 1,000 distant earthquakes. In 2023, scientists made a breakthrough discovery, a background hum permeating the entire universe, detected not by listening, but by watching the precise flickers of dead stars called pulsars. Pulsars are nature's most accurate clocks, spinning neutron stars that beam radio waves at such predictable intervals. They rival atomic timekeeping. For decades, astronomers used them to track everything from planetary orbits to Einstein's theory of relativity. But then something odd happened. By monitoring dozens of pulsars across our galaxy, researchers noticed their signals weren't quite as regular as they should be. The pulses arrived a fraction of a second early or late, as if space-time itself were stretching and squeezing in a slow, rhythmic dance, the culprit. A chorus of gravitational waves, likely from countless pairs of supermassive black holes spiraling toward collision in distant galaxies. Think of it like standing in a room filled with tuning forks. Each black hole pair emits its own distinct frequency as they orbit one another, creating waves that stretch spacetime. Alone, these signals are too faint to detect. But together, they merge into a cosmic murmur, a background hum that's been resonating for billions of years. This isn't the sharp chirp of individual black hole mergers like those picked up by LIGO. It's more like the static between radio stations, a low-frequency buzz that fills the universe. What's astonishing is the scale of these collisions. Each contributing pair consists of black holes millions or even billions of times the mass of our Sun, orbiting so close they'll eventually merge in spectacular explosions of energy. Yet because the universe is so vast, their gravitational waves overlap, blending into this steady hum. It's as if every supermassive black hole in existence is adding its voice to a choir we're only now learning to hear. This discovery opens an entirely new window onto the cosmos. Just as the cosmic microwave background gives us a snapshot of the infant universe, this gravitational wave background could reveal the hidden lives of black holes across cosmic time. Future telescopes, like the planned Laser Interferometer Space Antenna, will tune into these waves with even greater precision, potentially uncovering mergers from the universe's earliest epochs. One day, we might even decode individual contributors to this hum, pinpointing the locations of invisible black holes lurking in the void. Until then, the mere existence of this universal vibration reminds us space isn't empty. It's alive with the aftereffects of titanic collisions, a quiet drumbeat echoing from the darkest corners of creation. Earth doesn't just have one moon, it has secret companions, tiny celestial hitchhikers that dance around our planet in bizarre, looping orbits without us even noticing. One of them, a faint asteroid called Kamalulwa, is barely the size of a Ferris wheel, yet it's been Earth's quiet cosmic neighbor for at least a century. Unlike the Moon, which follows a neat, elliptical path, Kamalulwa weaves a wild, corkscrew-like orbit around the Sun, synchronized with Earth in a gravitational waltz that keeps it perpetually nearby. Some astronomers call these objects quasi-satellites, not true moons, but close enough to feel like part of the family. What makes Kamalulwa so fascinating isn't just its orbit, but where it might have come from. Spectral analysis suggests its composition is eerily similar to lunar rock, leading to a jaw-dropping theory. This could be a chunk of the Moon itself, blasted into space by an ancient asteroid impact. Picture a violent collision billions of years ago, sending debris hurtling into the void, only for one fragment to get caught in Earth's gravitational embrace. If confirmed, it would mean we've had a piece of the Moon trailing us all along, hiding in plain sight. These quasi-satellites aren't permanent guests. Their orbits are unstable, influenced by the tug of other planets and the Sun's gravity. Kamalulwa, for example, will likely break free within the next 300 years, drifting off into the solar system like a lost traveler. Others, like the asteroid 2023 FW13, recently discovered to have been orbiting Earth since at least 100 BC, follow such stretched-out paths that they spend millennia as Earth's distant shadows before finally slipping away. Why does this matter? Because these mini-moons are cosmic time capsules. Studying them could unlock secrets about the Moon's formation, Earth's early bombardment history, or even the origins of water on our planet. Some might even become targets for future space missions, offering stepping stones for exploration deeper into the solar system. So the next time you gaze at the Moon, remember, it might not be the only one up there. Hidden in the darkness, faint companions circle our world, silent witnesses to the ever-changing dance of gravity and time. Every 11 years, the Sun does something extraordinary. It flips its magnetic poles like a cosmic light switch. North becomes south, south becomes north in a process that isn't just some celestial quirk. It's a fundamental reset of our star's entire magnetic architecture. Right now, we're barreling toward the next reversal, expected around 2025, and when it happens, the effects will ripple across the solar system in ways both beautiful and disruptive. This isn't a sudden event, it's a slow-motion transformation. Picture the sun's magnetic field as a tangled web of invisible lines stretching into space. Over the solar cycle, sunspots, those dark, cooler patches on the sun's surface, emerge near the equator, carrying pockets of twisted magnetism. As they multiply, they drag the sun's magnetic field into chaos like threads in a knotted sweater. Eventually, the field weakens, fractures, and reorganizes itself, flipping polarity in a grand cosmic reset. NASA solar dynamo models show this isn't random. It's as predictable as clockwork, driven by the churning plasma deep within the sun's interior. But here's where it gets fascinating. This flip isn't just a solar spectacle, it affects us. As the magnetic field weakens before the reversal, the sun's protective bubble, the heliosphere, grows more porous. More cosmic rays, high-energy particles from deep space sneak through, bombarding Earth and posing risks to astronauts and satellites. Meanwhile, solar storms become more frequent, hurling charged particles that can disrupt power grids, knock out GPS signals, and paint the skies with auroras so vivid they've been seen as far south as the Caribbean. The most stunning side effect, auroras will ignite like never before. During the last polar flip in 2013, skywatchers reported shimmering curtains of light in places like Florida and Texas, rare treats usually reserved for polar regions. As the sun's magnetic turbulence sends charged particles spiraling down Earth's magnetic field lines, the atmosphere will light up like a neon canvas, offering front-row seats to a phenomenon usually confined to the Arctic and Antarctic. Yet for all its grandeur, the flip also exposes a vulnerability. The weakened magnetic field offers less shielding against galactic cosmic rays, particles moving at near light speed that can penetrate spacecraft and even pose cancer risks for astronauts. Solar observatories like NASA's, a solar dynamics orbiter, are now tracking these changes in real time, giving us forecasts for space weather much like meteorologists predict storms on Earth. What's truly mind-bending is that this cycle has continued uninterrupted for centuries, possibly longer. Ancient tree rings and ice cores contain traces of past solar activity, revealing that the sun's rhythm has held steady through civilization's rise and fall. And while the flip might sound apocalyptic, it's anything but. It's a reminder that our star is a dynamic, living engine, pulsing with cycles that connect everything from satellites to the shimmering lights above our heads. So when the next reversal comes, look up. The sky might just put on a show you'll never forget. Imagine a cosmic blender spinning so fast it could puree an asteroid in seconds. Now picture that blender weighing more than our sun, packed into a sphere the size of Manhattan. That's a neutron star for you, nature's most extreme physics lab, where matter gets crushed into such dense perfection that a teaspoon of it would weigh 1 billion tons on Earth. But here's what really bends the mind. Some of these stellar corpses rotate at 700 revolutions every second, their surfaces whipping around at nearly 1/4 the speed of light. That's not just fast, it's violent enough to warp spacetime itself. These ultra-fast spinners, called millisecond pulsars, are born from stellar catastrophes. When a massive star collapses in a supernova, its core compresses into a neutron star, preserving the original star's angular momentum in a package 100 trillion times smaller. It's like a figure skater pulling their arms in during a spin, except instead of twirling gracefully, this skater is a 20-kilometer-wide atomic nucleus spinning faster than a kitchen blender on its highest setting. The fastest known pulsar, PSRJ 1748-2446 AD, clocks in at an absurd 716 rotations per second, so rapid that if it had a mountain, even 1 millimeter tall, the centrifugal force would fling it into space. What makes these cosmic tops truly remarkable isn't just their speed, it's their precision. Pulsars beam radiation from their magnetic poles like interstellar lighthouses, and as they rotate, these beams sweep past Earth with metronomic regularity. Some pulsars keep time more accurately than atomic clocks, varying by less than 100 trillionths of a second per day. This precision isn't just a cool party trick, it's revolutionizing physics. When astronomers detected the first binary pulsar system in the 1970s, the subtle changes in its pulses provided the first indirect evidence for gravitational waves, confirming Einstein's predictions decades before direct detection was possible. But the real game changer, these stars might one day guide humanity to other solar systems. NASA's nicer experiment has already tested using pulsars as cosmic GPS beacons. By tracking the precise arrival times of their pulses, spacecraft could triangulate their position in the galaxy with kilometer-scale accuracy, no Earth-based signals required. Imagine a future where starships navigate the void using the steady ticks of these dead stars, turning the galaxy's most violent objects into signposts for exploration. Yet neutron stars aren't just tools, they're boundary pushers. At their cores, matter gets compressed into states so exotic that protons and electrons merge, forming a superfluid sea of neutrons and quark-gluon plasma. The surface gravity is so intense that if you dropped a marshmallow from just 1 meter up, it would hit the ground at half the speed of light, and their magnetic fields, 1 trillion times stronger than Earth's, enough to rip the electrons off atoms from 1,000 kilometers away. In the end, these spinning marvels are more than just cosmic oddities. They're natural laboratories, timekeepers, and maybe even the lighthouses of our interstellar future, all while defying everything we thought we knew about the limits of physics. So the next time you hear about a neutron star, remember, you're not just looking at a dead star, you're witnessing the universe's ultimate daredevil spinning on the edge of possibility. The largest water reservoir in the universe isn't on Earth or even in our galaxy. It floats 12 billion light-years away, wrapped around a feeding black hole at the heart of a distant quasar. This cosmic oasis holds 140 trillion times more water than all of Earth's oceans combined, enough to drown every planet in the Milky Way 1 billion times over. And here's the kicker, it exists as vapor, a vast, swirling cloud of superheated steam stretching hundreds of light-years across, held in place by the quasar's monstrous gravity. Quasars are among the most energetic objects in the cosmos, black holes so voracious they outshine entire galaxies as they devour surrounding matter. The water cloud surrounding this particular quasar, known as APM 08279 plus 5255, isn't just a cosmic oddity, it's a critical player in the quasar's violent life cycle. As gas and dust spiral toward the black hole's event horizon, friction heats the material to millions of degrees, releasing torrents of radiation. Water molecules in the cloud absorb this energy, then re-emit it as microwave frequency light, acting like a cosmic pressure valve that helps regulate the quasar's chaotic feeding frenzy. But how does water even form in such an extreme environment? The secret lies in the unique chemistry of quasars. In the outer regions of the cloud, temperatures drop just enough for oxygen atoms forged in the hearts of long-dead stars to bond with hydrogen, creating water molecules. It's a delicate balance, too close to the black hole, and the heat rips the molecules apart, too far, and the density is too low for them to form. This Goldilocks zone creates a sprawling, steamy atmosphere where water exists in quantities so vast it defies human comprehension. What's even wilder is that this water isn't just sitting there. It's part of a dynamic system driving the quasar's evolution. The microwave radiation emitted by the vapor acts like a cosmic brake, slowing the infall of matter and shaping the accretion disk around the black hole. In a way, this interstellar steam engine is both a byproduct of the quasar's violence and a force that moderates it, a feedback loop written in the language of physics and chemistry. And here's the real twist. This discovery hints that water might be far more common in the early universe than we ever imagined. If quasars can harbor reservoirs this vast, then smaller galaxies, perhaps even the primordial clouds that birthed the first stars could have been water-rich from the beginning. That raises tantalizing questions. Could water have been a catalyst for life's ingredients long before Earth existed? Might these distant vapor clouds hold clues about how the building blocks of planets and even life were distributed across the cosmos? For now, the quasar's water remains a breathtaking reminder of the universe's ability to surprise us. It's a place where the familiar, something as simple as H2O, exists on an unimaginable scale, woven into the fabric of one of nature's most destructive phenomena. And as we peer deeper into the cosmos, who knows what other hidden reservoirs we'll find, waiting in the dark to rewrite our understanding of water's cosmic story. We think of snow as something delicate and crystalline, made of frozen water drifting gently through chilly mountain air. But on Venus, the rules are turned upside down there. The snow is metal. Not the soft white flakes we know, but a bizarre precipitation of pyrite and galena, minerals that form glittering metallic caps on the planet's highest peaks. This isn't just a poetic metaphor, it's a real geological phenomenon, one that makes Venus even stranger than we ever imagined. The discovery came from an unlikely source, radar. Venus's thick, toxic atmosphere, a crushing blanket of carbon dioxide and sulfuric acid clouds, makes it impossible to see the surface with ordinary cameras. But when NASA Magellan probe mapped the planet in the early 1990s using radar, it revealed something astonishing. The tallest mountain ranges, like Maxwell Montes, showed unusually bright reflections at their summits, as if they were coated in something highly reflective. At first, scientists thought it might be fresh volcanic deposits or some strange weathering effect. Then, laboratory experiments and atmospheric models pointed to something far more exotic: metallic snow. Here's how it works. Down in Venus's lower atmosphere, where temperatures soar to 460 degrees Celsius and pressures are 90 times Earth's, minerals like pyrite, fool's gold, and galena, lead sulfide, can actually vaporize, rising as metallic mist into slightly cooler high-altitude zones. When these vapors hit the chillier mountain peaks, still scorching by Earth standards, but relatively cold for Venus, they condense into tiny metallic crystals, frosting the summits like some hellish version of a ski resort. The result, mountains that gleam as if dusted with glitter, their tops reflecting radar signals like cosmic disco balls. The contrast with Earth couldn't be sharper. Our snow forms when water vapor freezes into ice crystals, drifting down through freezing air. Venus's snow is born in a furnace, forged from vaporized metals that only solidify when they encounter the slightest temperature drop. It's a reminder of how alien Venus truly is, a world where lead falls like rain, where mountaintops shimmer with fool's gold, and where even the weather defies everything we know. But the wildest part, this metallic snow may not be unique. Some scientists speculate that similar processes could occur on other rocky worlds with dense atmospheres, like Jupiter's moon Io, or even exoplanets orbiting close to their stars. Venus, it turns out, isn't just a cautionary tale about runaway greenhouse effects. It's a laboratory for the weirdest chemistry in the solar system. And every time we peel back another layer of its mysteries, we're forced to rethink what's possible. So the next time you see snowflakes falling, remember, somewhere out there, a mountain range glitters with metal, proof that the universe never runs out of surprises. The Milky Way isn't just a majestic spiral of stars, it's a cosmic predator, silently devouring its smaller neighbors to fuel its growth. Over billions of years, our galaxy has grown not just by forming new stars, but by tearing apart and absorbing dwarf galaxies that stray too close, leaving behind ghostly trails of stars like crumbs from a celestial feast. The most striking example, the Sagittarius dwarf spheroidal galaxy, a tiny satellite galaxy caught in the Milky Way's gravitational grip. Right now, it's being stretched into a looping stream of stars that wraps around our galaxy like a cosmic serpent. Its remains scattered across the sky in a silent testament to the Milky Way's insatiable appetite. Thanks to missions like ESA's Gaia spacecraft, we can now map these stellar streams with stunning precision. Gaia's detailed charts reveal ribbons of stars, some as thin as spider silk, others stretching hundreds of thousands of light years, all that remains of galaxies torn apart by tidal forces. These aren't just random streaks, they're forensic evidence of the Milky Way's violent history. One particularly haunting structure, called the Gaia sausage, is the debris of a dwarf galaxy that collided with the Milky Way 8 to 10 billion years ago. The impact was so cataclysmic it reshaped our galaxy's core, leaving behind a dense, sausage-shaped cluster of stars orbiting at bizarre angles. But the Milky Way isn't just a mindless destroyer, it's a recycler. The stars from these devoured galaxies don't disappear. They become part of our galaxy's fabric, enriching it with new elements and altering its structure. Some studies suggest up to half the stars in the Milky Way's outer halo might be stolen goods, snatched from smaller galaxies over eons. Even our Sun could owe its existence to one of these ancient mergers, its composition hinting at a turbulent past where galaxies clashed and merged. What's truly humbling is that this process isn't over. Right now, the Milky Way is locked in a slow-motion dance with the Large Magellanic Cloud, a nearby dwarf galaxy that's destined to meet the same fate. Simulations show that in about 2.5 billion years, the LMC will plunge too close, triggering a violent disruption that could warp our galaxy's pristine spiral arms and spark a frenzy of new star formation. And beyond that, the ultimate galactic feast looms: the impending collision with Andromeda, which will see both galaxies merge into a single, colossal entity, their stars reshuffled like grains of sand in a cosmic hourglass. So the next time you gaze at the Milky Way's shimmering band across the night sky, remember, you're not just looking at a collection of stars, you're witnessing the aftermath of a billion-year feeding frenzy, a celestial empire built on the bones of its neighbors, and one that's still growing hungrier by the day. In space, even crying defies the laws of gravity. When astronauts shed tears, they don't roll down their cheeks. They pool into shimmering, quivering bubbles that cling stubbornly to their eyes like liquid marbles. Without gravity to pull them downward, tears accumulate into surreal, floating globes that distort vision until they're manually wiped away or shaken free. It's a hauntingly beautiful phenomenon, but beneath the surface lies something far more concerning. These trapped tears could be clues to a medical mystery plaguing long-duration space travelers' vision impairment that might permanently alter human eyesight beyond Earth. NASA first noticed the problem during extended stays on the International Space Station. Astronauts reported blurry vision, and medical exams revealed startling physical changes: flattened eyeballs, swollen optic nerves, and even permanent retinal damage in some cases. The condition, now called spaceflight-associated neuro-ocular syndrome (SANS), affects nearly 2/3 of astronauts who spend months in microgravity. Scientists believe it's linked to fluid redistribution without gravity. Bodily fluids like blood and cerebrospinal fluid drift upward, pooling in the head and increasing pressure on the optic nerve. Those eerie, unmoving tears, they're just the visible tip of a systemic shift happening inside astronauts' bodies. The implications are staggering. If unchecked, SANS could jeopardize future missions to Mars, where crews would spend years in microgravity. Imagine arriving on the red planet only to find your vision so degraded you can't read instruments or spot surface hazards. Current countermeasures, like thigh cuffs to draw fluids downward, and strict exercise regimens only partially mitigate the risk. Some astronauts return to Earth with irreversible changes, their eyes subtly reshaped by months in orbit. But here's what's truly fascinating. Studying these space-induced vision changes could unlock breakthroughs for Earth-bound medicine. The same fluid dynamics that harm astronauts' eyesight mirror conditions like idiopathic intracranial hypertension, where pressure builds around the brain. By unraveling how microgravity triggers SANS, researchers might discover new treatments for patients suffering from similar disorders. So the next time you wipe away a tear, take a moment to appreciate gravity's unseen role in that simple act. Out there among the stars, something as primal as crying becomes a scientific puzzle, one that could redefine human health both in space and on Earth. And as we venture farther from our planet, solving it might be the key to seeing our way forward. On a planet called HD 189,733b, the skies don't just rain water, they rain glass. Not delicate falling shards, but hyperviolent storms of molten silicate particles hurtling sideways at speeds up to 8,700 kilometers per hour. That's 7 times the speed of sound, a tempest so fierce it could strip flesh from bone in seconds. This cobalt blue hellscape, located 63 light-years away in the constellation Vulpecula, isn't just an exotic oddity, it's a laboratory for some of the most extreme weather in the known universe. At first glance, HD 189,733b might look deceptively serene. Hubble Space Telescope observations revealed its deep azure hue, reminiscent of Earth's oceans seen from space. But that's where the similarities end. The planet's vivid color comes not from water, but from high-altitude clouds rich in silicate particles, tiny fragments of molten rock and glass that scatter blue light. Below these shimmering clouds, the atmosphere churns with winds powerful enough to outpace a hypersonic jet, creating a perpetual sandblasting effect on a planetary scale. What makes this world so volatile? It's all about proximity. HD 189,733b orbits its host star at just 1/30th the distance between Earth and the Sun, locked in a gravitational embrace so tight a year lasts barely 2 Earth days. The star's intense radiation heats the planet's atmosphere to over 900 degrees Celsius, hot enough to vaporize rock into the silicate haze that gives the sky its color. But here's the twist: the planet is tidally locked, meaning one side always faces the star while the other languishes in eternal darkness. This extreme temperature difference, thousands of degrees between day and night, fuels hurricane-force winds that race from the scorching day side to the frigid night side, carrying clouds of glassy dust in a relentless, planet-spanning tempest. Imagine standing on this world. If you could survive the heat and the razor-sharp winds, the horizon would glow an eerie blue with sideways streaks of molten glass slicing through the haze like artillery fire. The ground, if it exists at all beneath the thick atmosphere, might be littered with microscopic glass beads, the remnants of countless storms fused together by the planet's brutal conditions. And if you listened closely, though sound can't travel in space, the constant roar of those supersonic winds would dwarf anything ever experienced on Earth. Yet for all its fury, HD 189,733b is more than just a cosmic curiosity. Studying its atmosphere has given astronomers unprecedented insights into exoplanet weather systems. By analyzing how light filters through its silicate clouds, scientists can decode wind patterns, temperature gradients, even the size of its glass particles, all from 63 light-years away. This research isn't just about understanding one world. It's about mapping the diversity of planetary climates, revealing how exotic weather shapes worlds beyond our solar system. The deeper lesson, HD 189,733b, shatters our assumptions about what a planet can be. Earth-like conditions, temperate climates, gentle rains might be the exception rather than the rule in a universe teeming with storms of molten rock, diamond blizzards, and skies that rain glass sideways. Every time we discover a world like this, we're reminded the cosmos doesn't care about what we consider normal. It operates on a scale of violence and beauty we're only beginning to comprehend. The moon isn't the silent, lifeless world it appears to be. Beneath its dusty surface, it shakes, rattles, and rolls with moonquakes tremors that can last up to 10 times longer than earthquakes here on Earth. Thanks to seismometers left behind by Apollo astronauts, we've learned these lunar tremors come in 4 distinct flavors, each revealing a hidden side of our closest celestial neighbor. The most common moonquakes are deep, rumbling events originating 700 kilometers below the surface. These aren't caused by tectonic plates, the moon doesn't have any, but by Earth's relentless gravitational pull. Just as our planet's gravity tugs on oceans to create tides, it also stretches and compresses the moon's rigid interior. Over time, this tidal friction builds up stress until the rocky mantle cracks like an overbaked cookie, releasing deep, low-frequency vibrations that can last for hours. Imagine holding a tuning fork against a massive bell. The moon rings in much the same way, its brittle crust resonating with slow, eerie tremors. Then there are the shallow moonquakes, far more violent but mercifully rare. Clocking in at magnitudes up to 5.5 on the Richter scale, these surface-level shakers are strong enough to topple hypothetical lunar structures. Scientists suspect they're caused by the moon's gradual cooling and contraction. Over billions of years, the lunar interior has lost heat, causing the crust to wrinkle like a raisin drying in the sun. When these wrinkles grow too severe, the surface suddenly shifts, triggering quakes powerful enough to send dust avalanches cascading down crater walls. Meteor impacts add another layer of chaos. Unlike Earth, the moon lacks an atmosphere to burn up incoming space rocks, so even small asteroids slam into the surface unimpeded. Each impact sends seismic waves rippling through the regolith, creating brief but detectable tremors. Apollo seismometers picked up everything from pebble-sized strikes to the 11-ton Taurid meteoroid that hit in 1972, a collision so forceful it registered as a magnitude 3 moonquake. The final type is perhaps the most bizarre thermal moonquakes. Every 2 weeks, as the lunar surface transitions from blistering daylight to freezing night, the temperature swings 300 degrees Celsius. This extreme heating and cooling causes the crust to expand and contract, producing tiny, predictable tremors at sunrise and sunset like clockwork. It's as if the moon itself breathes, exhaling seismic sighs with every dawn and dusk. What's fascinating is how differently these quakes behave compared to Earth's. Without water or atmosphere to dampen vibrations, seismic waves travel farther and linger longer, sometimes ricocheting through the moon's interior for hours. Apollo data even revealed the moon has a partially molten core, surrounded by a fractured layer of rubble that acts like a seismic echo chamber. Now, new missions are gearing up to listen even closer. NASA's upcoming Farside Seismic Suite will deploy advanced seismometers to the moon's far side, an area never before monitored for quakes. Combined with lunar orbiters mapping surface fractures, these tools could finally answer burning questions. Is the moon still geologically active? Could moonquakes threaten future bases? And what secrets do these tremors hold about the moon's violent past? For now, one thing's certain. The moon is anything but dead. It's a dynamic, shifting world whispering its secrets through tremors and quakes. And every vibration carries clues, not just about our celestial companion, but about the early solar system itself. So the next time you gaze up at that tranquil silver disk, remember, beneath the dust, the moon is alive with echoes. What if everything you see, the stars, the planets, even your own hands, is nothing more than an illusion? That's the radical idea behind the holographic principle, a theory suggesting our three-dimensional universe might actually be a projection, like a cosmic movie screen, encoded on a distant two-dimensional surface. Think of it like a credit card hologram. Tilt it and a 3D image appears, but the real information is stored flat. Now imagine that on the scale of the entire cosmos, where every galaxy, every black hole, every atom is just data painted on the universe's outermost boundary. This isn't science fiction, it's a serious hypothesis born from the clash between quantum mechanics and gravity. In the 1990s, physicists discovered something startling. The information needed to describe everything inside a region of space could fit on its surface area, not its volume. It's as if the universe runs on a cosmic zip file, compressing 3D reality into a 2D code. The math even suggests black holes might work this way. When matter falls in, its information isn't lost. It's imprinted on the event horizon like a fingerprint, preserved in a form we don't yet understand. But how could we possibly test such a wild idea? Enter quantum gravity experiments like GEO 600, a German gravitational wave detector. In 2008, researchers detected unexpected noise in their dated tiny, inexplicable fluctuations at the smallest scales. Some theorized this could be evidence of spacetime's pixelated nature, like static on a TV screen revealing its underlying resolution. If true, it would mean the smooth universe we perceive is actually built from discrete holographic bits far smaller than atoms. The implications are staggering. If the holographic principle holds, it would rewrite our understanding of reality itself. Time and space might emerge from something more fundamental, like a 3D image rendering from code. Even stranger, it could mean the universe has a built-in limit on information density, a cosmic storage cap forcing us to rethink everything from black holes to the Big Bang. Yet the most mind-bending part isn't the science, it's the philosophy. If we're living in a hologram, who or what is the projector? Is the universe self-encoding, or could there be layers of reality beyond our perception? For now, these questions remain unanswered, but every experiment brings us closer to the truth. One day, we might look back and realize the cosmos was never what it seemed, just shadows dancing on the walls of a higher dimensional cave. Jupiter's Great Red Spot isn't just a storm, it's a dying titan. For over a century and a half, astronomers have watched this colossal vortex, once wide enough to swallow 3 Earths side by side, slowly shrink into a shadow of its former self. Back in the late 1800s, measurements pegged its diameter at a staggering 40,000 kilometers. Today, it's barely 16,000 kilometers across, and high-resolution images from NASA, a Juno spacecraft, reveal a storm that's not just shrinking but changing shape. Its once proud oval twisting into something more like a misshapen pancake. What's causing this centuries-old tempest to fade? The answer might lie in Jupiter's chaotic atmosphere. Unlike Earth storms, which feed off ocean heat and dissipate within weeks, the Great Red Spot is a high-pressure system powered by jets of gas swirling at speeds over 430 kilometers per hour. These jet streams act like conveyor belts, feeding the storm energy from Jupiter's deeper layers. But something's disrupting that flow. Juno's measurements suggest smaller vortices, like atmospheric mosquitoes, are nibbling at the edges of the storm, stealing its momentum and chipping away at its structure. Thermal images even show the spot's core, once a uniform cauldron of fury, now fragmented into irregular patches, as if the storm is unraveling from within. Yet the Great Red Spot isn't going quietly. Recent observations reveal it's growing taller even as it narrows, stretching vertically like taffy pulled from both ends. Some scientists think this could be a last-ditch effort to conserve energy, trading width for height as the storm fights to maintain its identity. Others argue it's a death rattle, the final throes of a phenomenon that's dominated Jupiter's face since before telescopes existed. Historical records hint this might not be the first time the spot has changed. Sketches from the 17th century describe a much larger, paler oval, suggesting the storm we see today could be the shrunken remnant of an even more ancient monster. The Juno mission has brought us closer than ever to solving the mystery. Flying just 9,000 kilometers above the spot's crimson clouds, its instruments have mapped the storm's routes, plunging 300 kilometers deep, far deeper than Earth's oceans. This discovery upended old theories that the spot was a shallow weather feature. Instead, it's a planetary-scale wound, a cyclone drilling into Jupiter's gaseous interior. But even that depth might not save it. Computer simulations show the spot could vanish entirely within our lifetimes, collapsing into a string of smaller storms or dissolving into Jupiter's turbulent bands. The bigger question isn't just about Jupiter. It's about what the spot's fate tells us about giant planets everywhere. If a storm this powerful can weaken, what does that mean for the mega hurricanes on gas giants light years away? The Great Red Spot has been a cosmic constant for generations, a fixture in textbooks and telescopes. Watching it fade is like witnessing the end of an era, a reminder that even the mightiest forces in the universe are temporary. So while it lasts, cherish every image, every dataset, because one day, Jupiter's most famous feature might only exist in history books. Some stars hold secrets that defy our understanding of time itself. Take HD 140283, nicknamed the Methuselah star, a faint, unassuming speck in the constellation Libra that's rewriting cosmic history. When astronomers first measured its age, they were shocked. This ancient relic appeared to be 14.5 billion years old. There's just one problem: the universe itself is only 13.8 billion years old. How can a star exist before the cosmos it calls home? This cosmic paradox starts with the Methuselah star's composition. Unlike younger stars brimming with heavy elements forged in supernova, this one is almost pure hydrogen and helium, the primordial ingredients of the early universe. Its lack of heavier metals suggests it formed from nearly pristine gas, making it a time capsule from the dawn of creation. By studying its brightness, temperature, and nuclear fuel consumption, scientists initially calculated an age that clashed with everything we knew about cosmic chronology. But here's where the plot thickens: stellar ages aren't set in stone. Refined measurements accounting for the star's distance, oxygen content, and subtle pulsations have since adjusted its age downward to around 13.7 billion years, just shy of the universe's birthday. The key to solving this riddle lies in the uncertainties of stellar physics. Tiny errors in estimating the star's distance or internal mixing can skew age calculations by billions of years. Even the expansion rate of the universe itself, a hotly debated figure, plays a role in dating these ancient objects. The Methuselah star isn't alone in challenging our cosmic timeline. Other relics, like the even older SMSS 0313-6708, push the boundaries of what we thought possible in the early universe. These aged survivors suggest the first stars ignited astonishingly fast after the Big Bang, perhaps within just 100 million years, blazing to life in a universe still hot and dense enough to accelerate their formation. What's truly humbling is realizing how much we don't know. Each measurement, each recalibration, peels back another layer of cosmic history, revealing a universe more dynamic and mysterious than we ever imagined. The Methuselah star isn't just an anomaly, it's a reminder that the cosmos still holds puzzles we're only beginning to decode. And every time we think we've pinned down the universe's age, the stars whisper back, "Think again." Mars doesn't just have dust storms, it has apocalyptic dust storms, planet-engulfing tempests that can rage for months, turning the entire sky into a choking, rust-colored haze. Take the massive storm of 2018, a global monster that grew from a local disturbance in June until, by July, it had swallowed Mars whole. For weeks, sunlight couldn't penetrate the thick, swirling dust, plunging the surface into perpetual twilight. NASA Opportunity rover, a veteran explorer that had survived 14 years of Martian winters and scorching summers, met its end in this storm. Starved of solar power, its batteries drained, and after 1,500 attempts to wake it, engineers finally declared the mission over. This wasn't just bad weather, it was a planetary-scale siege. What makes these storms possible? The answer lies in the stark differences between Mars and Earth. For starters, Mars has no oceans, no vast bodies of water to regulate temperatures or disrupt atmospheric circulation. On Earth, oceans absorb heat, distribute it evenly, and create predictable weather patterns that break up dust cycles. But Mars is a desert world, its thin atmosphere unable to hold heat, leading to extreme temperature swings that fuel violent winds. When sunlight heats the surface, pockets of warm air rise rapidly, lifting fine dust particles high into the atmosphere. Once there, these particles absorb even more solar energy, warming the air further and creating a feedback loop that can escalate a local dust storm into a global event in weeks. Another key factor, the dust itself. Martian dust is incredibly fine, as powdery as talcum, and electrostatic forces from the planet's dry environment make it cling stubbornly to everything. When winds kick up, this dust doesn't just blow around. It stays suspended for months, creating a thick, sun-blocking shroud that lingers long after the initial winds die down. Compare that to Earth, where rain and humidity quickly weigh down dust particles, pulling them out of the atmosphere. On Mars, there's no rain to wash the sky clean. The strangest part, these storms aren't just destructive, they're unpredictable. Unlike hurricanes or cyclones on Earth, which follow somewhat forecastable paths, Martian dust storms seem to emerge spontaneously, growing and merging in ways that still baffle scientists. Some theories suggest they're tied to seasonal changes, like the southern hemisphere's summer when Mars is closest to the sun and solar heating is most intense. Others point to the planet's complex topography, deep canyons, towering volcanoes, and vast plains that create wind tunnels and updrafts capable of launching dust into the atmosphere with terrifying efficiency. But here's the silver lining. Studying these storms isn't just about understanding Mars. It's a window into how planetary atmospheres evolve, how climate systems can spiral out of control, and even how Earth might have avoided such extremes. Scientists suspect Mars wasn't always this hostile billions of years ago. It may have had lakes, rivers, and a thicker atmosphere. Somewhere along the way, it lost its stabilizing forces, tipping into the dusty, storm-ridden world we see today. For future astronauts, this poses a serious challenge. A global dust storm could black out solar panels, obscure navigation, and even damage equipment with abrasive dust. NASA and other space agencies are already developing solutions, from nuclear-powered systems to dust-resistant coatings, knowing that survival on Mars means weathering the worst the planet can throw at us. So the next time you see a windy day on Earth, remember, somewhere out there, entire worlds are being reshaped by storms unlike anything we've ever seen. And as we prepare to step onto Martian soil, these dusty tempests serve as a stark reminder space doesn't just invite exploration, it demands resilience. Imagine the universe isn't just a random scattering of galaxies, but an intricate spiderweb, one so vast it connects everything in existence. This is the cosmic web, the hidden scaffolding of reality, a network of invisible threads woven from dark matter and hot gas stretching across billions of light years. It's not just a backdrop, it's the blueprint of the cosmos, the reason galaxies cluster like cities along invisible highways instead of drifting aimlessly through the void. The cosmic web was born from the faintest ripples in the early universe. Just after the Big Bang, microscopic quantum fluctuations, tiny differences in density, were stretched to cosmic proportions by inflation, the universe's explosive expansion. Over billions of years, gravity amplified these ripples, pulling dark matter into vast filaments interspersed with enormous, empty voids. Picture pouring syrup onto a plate and watching it form sticky strands. Now imagine that syrup is dark matter and the plate is the observable universe. Where those strands intersect, galaxies formed, drawn together like beads on a string. But how do we even know this web exists if it's mostly invisible? The answer lies in the glow of history itself. When the universe was just 380,000 years old, it released a burst of light. the cosmic microwave background that still echoes through space today. By studying subtle temperature variations in this ancient light, scientists can trace the seeds of the cosmic web, the faint fingerprints of structures that would later grow into galaxies. Modern telescopes like the Dark Energy Survey and the upcoming Euclid mission map this web indirectly, using the gravitational bending of light to reveal where dark matter's immense gravity warps spacetime itself. The most mind-bending part, this web isn't static, it's alive with motion. Galaxies don't just sit passively on these filaments, they slide along them like commuters on a cosmic subway, funneled toward massive intersections called galaxy clusters. Some clusters, like the Coma cluster, anchor hundreds of thousands of galaxies, each following the web's hidden currents. Even our own Milky Way is part of this dance, pulled toward the great attractor by filaments we can't see but know must exist. But the cosmic web isn't just dark matter's handiwork. The spaces between filaments are filled with hot, ionized gas, so sparse it's 1,000,000 times thinner than Earth's atmosphere, yet so vast it contains half the ordinary matter in the universe. This gas is the universe's lost treasury, a reservoir of raw material that's been hiding in plain sight. Only recently, with instruments like the Hubble Space Telescope, have we glimpsed its faint glow, backlit by distant quasars shining like headlights through fog. What's humbling is realizing how much of this structure we've missed until now. For centuries, astronomers saw galaxies as isolated islands. Today, we know each one is just a single stitch in a tapestry so enormous it defies comprehension. And somewhere in that tapestry, the cosmic web keeps growing, knitting new galaxies into existence with threads of dark matter and gas, spinning the universe's story one filament at a time. Saturn's rings are one of the most breathtaking sights in the solar system, glittering bands of ice and rock stretching 280,000 kilometers wide, yet barely thicker than a skyscraper is tall. But here's the unsettling truth, they're vanishing before our eyes. Thanks to NASA's Cassini spacecraft, we now know Saturn's iconic rings are disappearing at a rate of 10,000 kilograms every second, a silent cosmic downpour falling into the planet's atmosphere. At that pace, entire mountain ranges worth of material rain down daily, erasing the rings bit by bit. If this keeps up, scientists estimate Saturn could be completely ringless in as little as 300 million years, a blink of an eye in cosmic time. This phenomenon, dubbed ring rain, happens because of Saturn's powerful gravity and magnetic field. The rings aren't static, they're a dynamic, chaotic swarm of particles ranging from dust grains to house-sized boulders, all caught in a delicate balance between gravity's pull and their own orbital momentum. But the inner edges of the rings stray too close to Saturn's upper atmosphere, where charged water molecules get tugged downward by the planet's magnetic field. As these particles fall, they heat up, creating a glowing arc of ionized rain that streaks toward Saturn's poles like a cosmic waterfall. Cassini even detected this shower directly, spotting bands of charged water ice in Saturn's upper atmosphere, the final remnants of ring material meeting its fiery end. The irony is that Saturn's beauty is literally fueling its own destruction. The same reflective ice that makes the rings so dazzling also leaves them vulnerable. Sunlight doesn't just illuminate the rings, it charges their particles, making them responsive to Saturn's magnetic field and accelerating their demise. And it's not a gentle process. The rain isn't just water, it's a mix of organic molecules and silicates, a cocktail of compounds that might be altering Saturn's atmosphere in ways we're only beginning to understand. Some researchers speculate this influx could be responsible for unusual atmospheric bands, or even the planet's bizarrely hot upper layers, a mystery that's puzzled scientists for decades. Yet the rings aren't going quietly. Their death throes might be creating one last spectacle. As material spirals inward, collisions between particles become more frequent, triggering faint bursts of light that Cassini detected as ring meteoroids. These tiny impacts generate plumes of vapor, adding to the rain and accelerating the ring's destruction in a feedback loop of celestial erosion. The innermost D-ring, already faint and wispy, could be the first to vanish entirely, with the brighter B and A rings following over the next 100 million years. What's truly humbling is realizing how lucky we are to witness them at all. Saturn's rings might not be permanent. Some theories suggest they're relatively young, possibly forming just 100 million years ago when a moon or comet strayed too close and was torn apart by tidal forces. If that's true, we're living in a special sliver of cosmic time, catching the rings in their fleeting prime before they dissolve into Saturn's clouds forever. So the next time you see an image of Saturn's rings, remember, you're not just looking at a static snapshot. You're witnessing an ephemeral masterpiece, a temporary work of art painted in ice and dust, slowly washing away into the void. And long after they're gone, their legacy will linger, not in the sky, but in the very air of the planet they once adorned. The moon seems like a silent, solitary companion, barely more than a dusty rock floating in space. But hidden from plain sight, it has a secret, a long, wispy tail stretching hundreds of thousands of kilometers behind it like a cosmic comet. Unlike the fiery plumes we associate with comets, though, this tail isn't made of ice or dust. It's a faint stream of sodium atoms glowing softly as they drift away from the lunar surface, forming an ethereal veil that wraps around Earth itself. So how does a world without an atmosphere or weather produce a tail? The answer lies in relentless bombardment. Every day, tiny meteoroids slam into the moon's surface at unimaginable speeds, kicking up particles of sodium, an element found in trace amounts in lunar soil, and launching them high into space. Solar radiation then charges these atoms, pushing them into a narrow, elongated stream that points away from the sun, just like a comet's tail. What's wild is that this process isn't new. The moon has likely had this tail for billions of years, invisible until modern telescopes finally caught its ghostly glow, the best time to spot this phenomenon. During a new moon, while most people focus on the darkened lunar face, astronomers train their instruments on the opposite side of the sky, where the sodium tail creates a faint but measurable bright spot in Earth's upper atmosphere. It's not something you can see with the naked eye. This glow is about 1,000,000 times dimmer than the faintest star, but specialized cameras have captured it as a pale, diffuse smudge, like a street lamp seen through fog. What's truly bizarre is how this tail interacts with Earth. Our planet's magnetic field funnels some of these sodium particles into a temporary bridge between the moon and us, a filamentary connection that lasts a few days each month. Picture it, a nearly invisible river of atoms flowing silently from the moon to Earth, a cosmic link few even know exists. The implications go beyond mere curiosity. Studying this tail helps scientists understand how micrometeoroid impacts alter airless worlds, a critical clue for future lunar bases. It also offers a blueprint for detecting similar tails around exoplanets, tiny fingerprints that could reveal hidden moons in distant star systems. So next time you gaze at the moon, remember, it's not just a dead rock, it's a dynamic world with its own eerie halo, a silent traveler with a tail streaming behind it, whispering secrets about the universe we're only beginning to hear. Most planets orbit stars like obedient dancers in a cosmic ballet, but not all. Some are cosmic outcasts hurled into the void by gravitational chaos, left to wander the darkness alone. These rogue planets, untethered from any star, drift through the frigid emptiness of interstellar space, invisible to all but the most determined observers. One of the most famous, SIMP J013656663, is a Jupiter-sized beast roaming just 20 light-years away, with a magnetic field over 200 times stronger than Earth's, so powerful it generates shimmering auroras in its own atmosphere without a star to fuel them. How does a planet end up alone? The answer lies in the violent nursery of young star systems. When multiple planets form too close together, gravitational wrestling matches can fling the smallest or unluckiest worlds into the abyss. Others might be born in isolation, collapsing directly from gas clouds too small to ignite into stars. The result is the same, a rogue planet, untethered and untraceable by conventional means. SIMP J013656663, for example, emits no starlight, only the faint infrared glow of its own cooling heat, betraying its presence like a dying ember in the dark. The real intrigue, these wanderers might not be lifeless wastelands. Tidal forces from long-lost stars or radioactive decay could keep their interiors warm, creating vast subsurface oceans beneath icy crusts. Imagine Europa's hidden seas, but on a planet with no sun, drifting eternally through the void. Some scientists speculate that rogue planets could outnumber stars in the Milky Way, potentially hosting more liquid water than all of Earth's oceans combined. If life exists in these lightless depths, it would thrive in total darkness, sustained by hydrothermal vents or chemical reactions we've yet to imagine. Detecting these ghosts is a monumental challenge. Traditional planet hunting methods rely on spotting the wobble or dimming of host stars, useless for rogue worlds. Instead, astronomers use microlensing, where the planet's gravity briefly bends light from a distant star like a magnifying glass. Even then, catches are rare. SIMP J013656663 was only found because it's unusually hot and massive, a cosmic heavyweight leaving footprints in the dark. New telescopes like the Nancy Grace Roman Space Telescope aim to uncover smaller, Earth-sized rogues, potentially revealing a hidden population of nomads lurking between the stars. The implications are staggering. If rogue planets are common, they could serve as stepping stones for interstellar travel, dark, frozen waypoints offering resources or shelter in the endless void. Or they might carry life between stars, frozen microbes hitching rides on ice-covered worlds, seeding the galaxy like cosmic dandelions. For now, these solitary giants remain enigmas, their stories written in magnetic fields and infrared whispers. But every discovery peels back another layer of their mystery, forcing us to rethink what it means to be a planet and where life might hide in the universe's uncharted expanses. The sun isn't just a silent ball of fire, it sings, not with words or melodies, but with deep, resonant pulses that echo through its core like the heartbeat of a cosmic giant. Thanks to heliosismology, scientists can translate these vibrations into sound, revealing a chorus of low-frequency waves that resemble distant ocean swells or a continuous, rhythmic whooshing of solar wind. It's as if the sun is breathing, its surface rippling with pressure waves that travel inward, bounce off its dense core, and rebound outward in a symphony of nuclear physics. These sounds aren't random noise, they're the sun's way of broadcasting its internal secrets. Imagine dropping a pebble into a pond and watching the ripples. Now replace the pebble with a thermonuclear explosion and the pond with a plasma sphere 100 times wider than Earth. That's essentially what's happening here. Convection currents, the same process that makes boiling water swirl, churn beneath the sun's surface, generating pressure waves that propagate through its interior. By measuring the frequency and timing of these waves, astronomers can map the sun's hidden layers with astonishing precision, much like geologists use earthquakes to probe Earth's core. When scientists convert these solar oscillations into audible frequencies, the result is haunting. The dominant tones hover around 3 MHz, far too low for human ears to hear naturally, but when sped up by 42,000 times, they transform into a deep, resonant hum. Some describe it as the sound of a forest wind, others as the roar of a distant jet engine. NASA's Solar Dynamics Observatory has even captured songs from individual solar flares, their magnetic loops vibrating like plucked guitar strings, emitting eerie, metallic twangs amid the constant whooshing backdrop. What makes these sounds so valuable isn't just their strangeness, it's what they reveal. The sun's acoustic waves behave differently depending on temperature, density, and magnetic fields. By analyzing shifts in their pitch and speed, researchers can detect hidden sunspots before they emerge on the surface, track the movement of solar plasma, even predict violent solar storms that could threaten satellites and power grids. It's a stellar early warning system written in vibrations too subtle for any telescope to see. The most mesmerizing part, this isn't a static soundtrack. The sun's voice changes with its 11-year activity cycle. During solar maximum, when sunspots and flares peak, the whooshing grows more chaotic, layered with clicks and pops from magnetic explosions. In quieter periods, the tones smooth into a meditative drone. Ancient cultures worshipped the sun as a deity, but today we know it as something equally awe-inspiring. The universe's largest musical instrument, playing a concerto of fusion and gravity that we're only beginning to understand. So the next time you feel the sun's warmth, remember, you're basking in the glow of a star that doesn't just shine. It sings, a song written in the language of physics, echoing across 93 million miles of space to remind us that even the quietest corners of the cosmos are alive with sound. Time might seem like the most reliable constant in our lives, but in the grand scheme of the cosmos, it's anything but absolute. Out there, the universe keeps time in ways that defy human intuition, from the metronomic pulses of spinning neutron stars to the quantum jitters of atoms so precise they'll lose less than a second over billions of years. These aren't just natural curiosities, they're the scaffolding of reality itself. The invisible ticks and talks that shape everything from GPS satellites to the fate of galaxies. Take pulsars, nature's most unforgiving timekeepers. These ultra-dense stellar corpses spin hundreds of times per second, beaming radiation across space with a regularity that rivals atomic clocks. The fastest known pulsar, PSRJ 1748-2446 AD, whirls at a mind-numbing 716 rotations every second, so stable that its rhythmic pulses can predict celestial events millennia in advance. But here's the twist, even these cosmic precision instruments are warped by relativity. Orbiting a companion star, the famed Hulse-Taylor binary pulsars tick slow and speed up as it navigates the gravitational well of spacetime, proving Einstein right down to the millisecond. Then there's atomic time, the gold standard of human-made clocks. Cesium atomic clocks like NIST F2 in Colorado measure time by counting the oscillations of cesium atoms, 9, 192, 631, 770 vibrations per second to be exact. These clocks are so accurate they drift by just 1 second every 100 million years. Yet even they bow to the universe's whims. In 2020, scientists discovered that optical lattice clocks, which trap strontium atoms in laser grids, can detect gravitational time dilation from a single millimeter change in elevation. Step onto a stool and time literally ticks faster for your head than your feet. A reminder that time isn't just measured by the cosmos, it's shaped by it. But beneath these marvels lurks a deeper mystery. Is time fundamental or merely an illusion emerging from quantum chaos? Some physicists argue time is a bedrock property of the universe, as real as space or matter. Others propose it's a side effect of entropy, the universe's slide from order to disorder, like watching a shattered glass reassemble itself in reverse and calling that sequence past to future. The most radical theories suggest time might not exist at all at the quantum level, where particles interact without a clear before or after. Experiments with entangled particles show correlations that appear to defy causality, as if the universe hasn't decided yet which event comes first. This isn't just philosophical musing. If time is emergent, not fundamental, it could rewrite the laws of physics. Quantum gravity models like loop quantum theory treat spacetime as a network of discrete chunks that only create the illusion of continuous flow when viewed from afar, like pixels blending into a movie. Even black holes muddy the waters, their event horizons stretching time to a standstill from an outsider's view while passing normally for someone falling in. Which perspective is real? The answer might depend on where you're standing, or if standing even matters in a timeless quantum foam. So the next time you check your watch, remember, you're not just tracking minutes. You're tapping into a cosmic debate about the nature of reality itself, where neutron stars, atoms, and quantum voids all chime in with conflicting answers. The universe isn't just ticking, it's questioning what ticking even means. Every atom in your body, the oxygen in your breath, the iron in your blood, the calcium in your bones, was forged in the heart of a dying star. This isn't poetic exaggeration, it's cosmic fact. When Carl Sagan famously said, "We are made of star stuff," he wasn't speaking metaphorically. He was describing the literal alchemy of the universe, a process called supernova nucleosynthesis that transformed primordial hydrogen into the building blocks of life itself. Take a deep breath. That oxygen you just inhaled, it was created in the final convulsions of a massive star, one that lived fast, burned bright, and died in a cataclysmic explosion billions of years ago. The carbon that forms the backbone of your DNA, forged in the fiery cores of red giants where helium atoms smashed together under crushing pressure. Even the gold in your jewelry or the iron in your blood owes its existence to stellar violence. These heavy elements were born in the unimaginable heat of colliding neutron stars or the shockwaves of supernova, scattered across space like cosmic seeds. The periodic table isn't just a chemistry chart, it's a stellar obituary. Elements lighter than iron, like carbon and oxygen, were cooked slowly in stellar furnaces over millions of years. But elements heavier than iron, they required something far more extreme. When a massive star exhausts its fuel, it collapses inward in a fraction of a second, then rebounds in a supernova explosion so powerful it outshines entire galaxies. In that fleeting moment, the extreme temperatures and pressures fuse atoms into heavier elements, blasting them into the void. Without these explosions, the universe would lack the diversity of elements needed for planets or life. Here's the breathtaking part. This process isn't ancient history. It's still happening. Right now, stars are dying across the galaxy, enriching the cosmos with new material. The Crab Nebula, the remnant of a supernova witnessed on Earth in 1054, is still expanding, its filaments laced with sulfur, neon, and argon elements that might one day end up in someone's body a billion years from now. Even our solar system bears the fingerprints of multiple stellar generations. Meteorites contain isotopes like aluminum-26, proof they formed from the debris of long-dead stars. This cosmic recycling connects us to the universe in the most intimate way possible. The nitrogen in your muscles, the phosphorus in your bones, the sodium that carries nerve impulses, all of it was once part of something vast and luminous. When you look up at the night sky, you're not just an observer. You're the universe gazing back at itself, a collection of atoms that temporarily came together to wonder about their own origins. So the next time you feel insignificant under the starry expanse, remember, you're not separate from the cosmos. You are the cosmos, a living, breathing testament to the universe's ability to create, destroy, and recreate itself across the eons. And that's the most profound fact of all. From holographic projections encoding our reality to diamond planets glittering with trillions of carats of cosmic gemstones, the universe never stops defying expectations. We've explored black holes warping time itself, galaxies being devoured by our own Milky Way, and rogue planets wandering the void, each discovery proving reality is stranger than fiction. Whether it's the metallic snow frosting Venus's mountains or the great attractor dragging entire galaxies toward an unseen fate, every revelation peels back another layer of the cosmos' infinite mysteries. Think about it, we're made of stardust, breathing oxygen forged in supernova, while quantum vibrations hint that space-time itself might be pixelated. The moon is drifting away, Saturn's rings are vanishing, and stars hum like celestial tuning forks, proof that the universe isn't just a static backdrop. It's a living, evolving spectacle, and we're here for the front row seat. Now it's your turn. Which fact left you awestruck? Was it the universe's hidden 96%, or the thought of glass rain lashing a distant exoplanet at supersonic speeds? Drop your favorites in the comments, and while you're at it, tell us what cosmic mysteries we should explore next, because this isn't the end. Every question answered reveals 10 more waiting in the dark. So keep looking up, stay curious, and remember, the universe isn't just out there, it's within you.